Compound interest. Well, what we want to do is review where compound interest, well, we don't know what it is, but it comes from that exponential function to start with. And so we'll review all the equations that we have that are very similar. Um, so exponential functions, that's where we start. And that one was y equals a b to the x. And then we went to exponential growth, and that was our y equals a, which was our initial amount, and then our multiplier with the exponent of t, that makes it the exponential. And remember that the growth was 100% plus our rate, but they were in decimals. That's why it's 1 plus r. And then the exponential decay was very similar to that. So that would be a times 1 minus r, so that subtraction of the rate, which was less than 1, was a decay. And then we had simple interest. And that was y equals the p principal, which is basically the same as a, and it was a growth, because when you do interest, it's a growth. So that kind of matches up with our growth, so we can think of that as a growth, and that was to the t power. So it's basically the same as a growth one. It's just because it's banking, they like the p for principal in there, and then the rate is your annual rate, with a t usually being the annual. Now, compound interest is very similar to that. So, but it's a little bit different. We have our P for our principal, which is kind of that same A. We also have 100%, because we always have to have that 100%. And it's a growth. And it uses that T and the R as our rate, as the annual rate. Now, what's different about this is that in the equation we have our n, the number of times it's compounded. So that would be the compounding part. Now, once you multiply the number of times you do it for t, the time, you have to divide that rate by the same number, because you have to take that rate and divide it. Say if it was twice a year, that n would be 2 times a year. So we have to kind of take that rate and divide it into that same amount of twice a year. So we divide by 2 to get that. So we want to kind of mark that n is the number of times the interest is compounded per year. And usually it's per year. Sometimes it's per month, like T is months. That's more with a credit card, but most of the time it's per year. And actually the credit card is per year, but then they charge it per day, and it just gets really complicated. But this is the basic principle of that idea. So if we have an example, so our example 1, if we have $100 and we put it in as a 6% annual interest rate, and it is compounded monthly. So how we write that is we start with our y, and thinking of our initial principal, but they call it a principal P. So it's our starting, our y-intercept is that 100, that A, the P. And we always have to have, 100% of it in there to begin with. And we're going to take that 6%, so 0.06. Now that would be normally what we would do for that simple interest or growth up here, either if we think about it as that simple interest here or the growth here. It's basically the same thing, just a slightly different. But we're going to compound it monthly. And so T is the number of years. And we know it's number of years because it said annually, and annually means a year. So in that year, how many times do we compound it? That's 12 years. So we're going to do it 12 times every year. So that's what that 12T means. But at the same time, we have to divide our interest rate by those 12 times. So each 12 times. So we have to take that interest rate and divide it into that piece of that. So now if we want to simplify this, I know a lot of people are like, well, I'll grab my calculator. But you don't actually have to, because I noticed that 6 and 12 go into it nicely. So I can simplify 0.6 goes into 0.06.01 times, and 6 goes into 12 2 times. Now I can take half of 0.01 for 0.005 as my percentage, or my point, plus 1, all of that to the 12T. So don't forget to bring your T down. That 12 is compounded 12 times, and every month then it's 0.005 multiplier of that. So bring down my Y, bring down, so that is the formula, the equation for compounding it yearly. So if I wanted to know, say, in 2 years, I would put 2 in for T. So that would be Y equals 100 times 1.005. And then 12 times 2 is 24 times. So we're going to multiply that interest compounded each month 24 times, 12 each year. Now that's a little bit different than doing that simple interest. If we had done the 2 for the simple interest, that would be Y equals the 100 times 1.06 to the 2 times. So that 6% would be compounded, would be compounded twice in that year. So it's done once the first year, and then the second year it's done again, taking that little interest on the other interest. Now, when you have a compound interest, what that does is if it's done monthly, that means you're taking and doing it every month over that year. So instead of just doing it 6%, you're going to do that little bit each month for 12 times each month, and then do that for 2 years, and you're going to get more than if it was simple interest. So that's what that compounding interest, meaning within that time frame you're doing it more often. So now in example number 2, we are going to write equations. So when we write an equation, first off we need some data. So we'll start with our table, or be given a table. So 0, 1, 2, 3, 4, and 5. 100, 110, 121, 133.10, 146.41, 161.05. So what we notice here, I notice, is over here on the left-hand side, I have plus 1, plus 1, plus 1. So that means my x values are going up 1. And so we're going to write exponential equations. So I notice that it is a growth, so it's going to be more than 1. So to find our multiplier here, what we can do is take that number, and using our number sense, we can, oh, we've done this before, taking this bigger number, meaning the next one in bigger of the x, and divide it by the one previous. And when we do that, we get a multiplier of 1.1. Now, if we do that for the next one, 121 divided by the previous one, we get times 1.1. And if we do that for the third one, when we type that into the calculator, we get 1.1. So notice that I put a times in front of that because that's our multiplier. So that means that this is an exponential growth. So we're going to write our equation. We want to have y equals a b x. Now, I'm not using the 1 plus the percentage, which I could use, but I already have my multiplier. So this right here is my b. So I can put that right in for my multiplier, which is b, the multiplier. X is my exponent. A is my y-intercept, and I can see that right here at the beginning of our table when x equals 0 and y equals that. And there is our function. And I can see it is a growth, so since I was thinking about it beforehand, this is a 10% growth because I can see the 100% plus that 10%. If we look at another table, so let's label this table A and this table B. If we have a slightly different one, 1, 2, 3, and 4. So our x values are going up by +1 for each one of those. So I know that if over here it can either be a linear, if it was a plus plus constant rate of change, or a minus minus minus, or if it's a multiplier, then it's an exponential. So given 64, the first one is 16, the second one is 4, third is 1, and 1/4. And I notice this pattern is times 1/4. Now don't think of it as a divide by 4, because remember, when we're writing our equation, we need our multiplier. So these are our multipliers. So I like to put in that times to help me realize that it's not a minus or a plus 1/4 plus 1/4 plus 1. It's a multiplier. So when we have our equation, y equals a, the initial, times our multiplier to the x power, I can find my y-intercept right here, my start, my initial, my principal, 64. My multiplier is 1/4 x. And there's our equation for that. Now, I do know that this is a decay. So if the second part of this equation or question was, what is the percentage rate of decay? So I know it's a decay, and I want the percentage rate. So that means I need to kind of change this thinking now to help me 64 into that 1 minus, because we want that 100% minus. And that's the hard part about these ones, is that you have to think about that 100% minus your percentage here. So that would be, to get 1/4, I would have to subtract 3/4 away from 1, which then would be, as a decimal, 0.75. So that percentage would be 75% decay to get to that 1/4 multiplier. Our last problems are rewriting. equations. Well, exponential equations. So our first one that we'll do is y equals 100, kind of like 100, I guess, today. 0.96 t divided by 4. All right, so remember it's a fraction, so we have to kind of gear our thinking not only to exponential growth, but we have to go back to our exponents and think about how can we work with this to transform, to rewrite this. So y equals 100, and now that 0.96, and I'm going to think about that exponent because it would be easier to kind of work that out. I like that t to find out by itself. Would be kind of nice to have that t by itself. So I'm going to multiply that by 1/4 because that's equivalent to 1/4. T over 4 is equivalent to 1/4 times t. So now I'm going to think, oh, that 1/4 could go with inside. I could regroup it because it is just exponents. So 0.96 to the 1/4. And then I know that that 1/4 could be rewritten to a little easier for me to understand. The fourth root of that 0.96 to the power of t. And then when I take and type into my calculator with the fourth root, you might have to kind of search for how to do that. You want to pick an easy number like the fourth root of 64 is 2, or 4, I mean. No, yeah, 4. So, is it? No. The fourth root of, we could do threes. 3 times 3 is 9, and then 9 times 9 is 81. So the fourth root of 81 is 3. So we know that because 3 times 3 times 3 times 3, 4 times is 81. So in our calculator, we could try to figure out an easier one to do before we did a more complicated one here. Is get the keystrokes to get that answer 3, and then do the same thing with our decimal. And when we do that, we get the principal rate or the initial rate, and we get 0.99 as in our calculator. So we've simplified this down into just t by itself. That's that x, that O, which means that this is a decay because it's less than 1. And if I think about this 1 minus 100% minus 1%, so that would be a 1% decay, or our R percentage is 1%, and it is a decay. So our next example, let me erase our other little example, is a function. So f of t equals 1.1 t minus 3. So this is a little different than the other one. That one was a multiplier, so we could easily pull that out and change it to the fourth root. But this one's a little different. So I have to think about my other exponent properties and think about, well, so how do you get these two together by adding, well, let's do adding a negative. So when you add them together, so those exponents means we have to have the same base. So I'm thinking the same base, 1.1 is the same base, and they have to be a -3 and a t. So to add those together, I would get t minus 3. So now I want to think about, well, how do I deal with this negative exponent? Oh, I can take that negative exponent and put it in the denominator to make that exponent positive. So f of t equals, in the numerator, 1.1 to the t power over 1.1 to the negative 3 power. Oh no, it's positive now because I moved it down. So it's positive 3, which is what I like. So now when I take that and think about how do if I have, I usually don't leave this exponent in the denominator. So I have to think about, usually I want that, so similar to this one over here, we got it into y equals a b to the x power when it wasn't in that form. So we want to get that into that same form where a is in that numerator. So this right now is in the denominator, so I have to think about using my 1 over 1.1 to the third power. So I want to simplify that part because this 1.1 to the t power is fine. So when we take in a calculator and take 1 divided by this number that we type into that calculator, we get a pretty crazy number, 0.7513148809, I think it is. Ugh, that's a big number. But basically, we can then round it. And usually we round it to that 100th place. So f of t, now when we round it, we're going to use the squigglies, is approximately 0.75 times 1.1 to the t power. So that 0.75 is our y-intercept, our a, our y-intercept of 0.75 where it crosses the y-axis. And here we have our rate is 10% and it is a growth. So when we look back at all the equations that we use, they are all very similar in structure. So they come from that exponential growth function, y equals ab to the x power, where b is our multiplier, a is our initial or y-intercept. And you can see that as we go down to the growth, the decay, the simple interest, and the compound interest, but they all include the r depending upon if it's a growth or a decay, plus or minus. They all have that t as the exponent. Now the tricky one is the compound because you have to do it. What compound is the number of times in that period, but then you have to take the rate at the same time and divide it. So really you're kind of doing multiplying by n of the exponent, and the inverse would be that dividing the rate by n.